Okay, the purpose of this video is just to quickly power through this review thing. I'm not going to emphasize a lot of the stuff at the beginning because you have read about that and done problems, and you have the ability to go back and check those problems with setups because I posted all the red problems with setups for you. So I'm just going to really go through this stuff pretty quickly. We talked of these diagrams are going to be the same ones in your book. I did want to mention a couple of the equations as we go through here. For instance, kinetic energy is 1/2 mv squared. That will be on your purple sheet, and your purple sheet will be the last page of your test. So you can just look that up, and there it is. Kinetic energy of a molecule equals 1/2 mv squared. So this is provided for you, so you don't have to memorize that one. And that also, if you look at what a joule is and how it's defined, there's your mass, kilogram, SI unit. Meters per second would be velocity, and 1/2 mv squared, there's your v squared, m squared over v squared, and that is defined as a joule. So make sure you know that. That's not on the purple sheet, and also this conversion is something they expect you to know, and you will be expected to know for the test. So you just commit that to memory. 4.184 joules in 1 calorie. Okay? And if you get like 4.18 and you can't remember what the last number is, you're definitely going to get partial credit for those kinds of things. But use this conversion, 4.184. Boom. Pound it in the old melon. Okay? Talked a lot about system and surroundings and heat and work. So you're just going to want to review some of this stuff. With first law of thermodynamics, really concentrate on this second part about how if a system loses energy, it must be gained by the surroundings and vice versa. Okay? So those are the kind of things that we want to be talking about. Now these delta E values, this one right here, just make sure you realize that you know that endothermic was negative, positive when you were talking about temperature and heat. So for the energy, the whole energy of the system, endergonic is when it is positive, and of course when it is negative it would be exergonic, just like when delta H is negative it's exothermic. Okay, so those kinds of things. We're just kind of reviewing some of the key ideas here. This little equation right here is important, and they do not have that one as part of the equations on the purple sheet. So delta E equals the heat plus the work. Now, this little table right here, I would really spend some time looking at. You know that Q is heat. The signs make a lot of sense for heat. If a system gains heat, it's positive. If it loses heat, it's negative. I don't even think you need to commit that to memory. That's so logical. However, work, be real careful with this one. Work done on the system, that W would have a positive value. You're going to need this for calculations on the test. And work done by the system is negative. Okay? I hate goodbyes. They're really negative. That's the silly, stupid way I remember that. Okay? Work done bye-bye, negative. I hate byes. The energy makes sense too, I think. A net gain would be a positive delta E. A net loss would be a negative delta E. So, but this, knowing these values and the terms that go along with them, going to be super useful for you on a couple of problems on the test here. We had talked about endothermic with regards to heat. So this is absorbing heat, feels cold to the touch. exothermic, giving off heat, feels warm. You can just feel that heat coming off of something that is exothermic. We talked about state functions with Hess's law, so I'm going to plow through this stuff pretty quickly. This is the same diagram in your book. One little trick here is that work, when you're talking about a gas, can be related to pressure units, which of course is force per unit area. Okay, so that will result in a change in volume. So that volume and pressure are going to come into play. We'll talk about that, with our gas laws and those things that we've kind of mentioned in earlier chapters here. So you can make this statement that work equals a negative pressure times the change in volume of a gaseous system here. Okay? So, when you do some rearranging of some equations, you can get at defining enthalpy, something along these lines, that it's going to have to do with heat and the pressure times the change in volume, which we just said back there is work. And what you can do is you can use this equation, which, by the way, that's one that you really want to know. Delta E equals heat plus work, and that'll relate to that table we had talked about, work done on the system, by the system. So when you're defining this part, it would be work done by the system, the minus W. But at any rate, we know that delta E is defined as heat plus the work, and you'll notice those W's will cancel right out, and then you're like, oh, well, enthalpy then, as fancy as it is basically the heat for these types of systems. So that works. And if you're at these constant conditions, we can use those interchangeably, and that's where that's why we'll talk about delta H as being Q, but it's not exactly the same thing, because you had to kind of do some derivation there in certain circumstances. So this you got down already: delta H positive, endothermic; delta H negative, exothermic. And then we're going to talk about enthalpies of the reaction. Now this is really important to hammer this idea down. This is going to come up on the next problem we're doing too. The heat of the products minus heat of the reactants is for the whole reaction, and that is actually written on your purple sheet, so you'll be able to see what that means as well. Okay, but we're going to get into this in more detail on the last section here. So you got this thing called enthalpy, and you guys have read and studied about this. One of the ways of, in the lab, figuring out what enthalpy is for an entire reaction is to take three things into account to really truly figure out the heat that is going on. And remember, we're using those kind of interchangeably. So yeah, you can figure out the heat of a reaction by just measuring the mass times the specific heat, that's what this small s stands for, times the change in temperature. Now this equation, the good news is it's on your purple sheet. The bad news is they use Q equals MC for specific heat. There was a movement to change that to S, and they changed their mind again and went back to C. But C and S mean the same thing there, and that's the specific heat, which, going back to this table, different things transfer heat differently. Metals, plastics have, metals can transfer that heat much faster, and insulators transfer the heat very, very slowly. Okay, so That's why you have to take that into account, and that's why temperature and heat aren't really the same thing. When you come to class, I have a little cool demonstration that I show the difference between heat and temperature, as we can see here. Okay, so calorimetry was one way. Hess's law, you did that nice packet. Hopefully everybody's feeling cool with that. Now, today's you're going to hopefully have already read about the enthalpies of formation, the delta H F. It's the heat of formation. You can do that for a whole reaction. Okay? Now, you're going to find this stuff in the back of your book. Okay? I want you to just take a look and remember this one, that carbon dioxide has a negative 393.5 value. Okay? So I'm just going to pause this and switch over to the Appendix C in the back of your book. So this is right in the back of your textbook, and at a given temperature, these are the values that it took to form these molecules or elements. So one of the interesting things to note about this, and is very important for the test, is that in their elemental pure form, they're going to be 0. Okay? So you can look at that. Here's a really good example. Br without the 2 on it has a value. Br gas has a value. But bromine as a liquid, which is the way it normally exists at 25 degrees Celsius, has a 0 value. So it takes no energy to form it. But I just wanted to show you that if you go to the back of your book, you can find these values. Now, this will be provided for you on the test, but when you're doing your worksheet, go back to page 1112. Okay, let's go back to the PowerPoint. Finish that up. Okay, so here's that same stuff that was in the back of your book, just a smaller version of that table, and it doesn't have the pure elements in there like it did. So this gets a little bit confusing, kind of relates to Hess's law, but I want to kind of do this a little quicker. What you can do is just add up all the products and subtract that from the reactants. This equation without the N and the M is on your purple sheet. So all you have to do is look up those values that we just talked about. And you're going to start with the products, and you'll get a chance to practice these guys. So notice there's a 3, and that's what they mean by stoichiometric coefficients. There's 3 CO2s. Now you remember that negative 393 value that we talked about. So you can just add that up. That's what that fancy summation symbol means. It just means you're just adding them up. So add up your 4 waters. You'll find that in the back of the book or on the test that'll be provided. And then you subtract the whole thing here. Be a little careful with order of operations here. You see we got brackets and parentheses. But when you do the math on this, you'll get the change in heat for the reaction, which will be negative 2219.9. So here, this was a crude experimental version, and it's right in the right ballpark. So yeah, just by looking up the individual things and taking the products minus the reactants, you were able to come up with that number. Okay, so this you'll get good at when you practice a couple and check your answers. But you got to know where those numbers come from, and that's Appendix C. And it mentions it in the problems too. So the energy in foods, that's fair game. Read that section. Don't spend a lot of time. I think there's maybe 1 or 2 multiple choice questions about this. But just look over and make sure you read that last section. Hopefully, by the time you're my age, this will be greater than 6%, this little yellow pi. I assume since this book has been printed, that's a little higher. But anyway, good luck on the test, and go get them.